Hi, I'm Brian with tutoring services down at the Learning Commons. Today I'm going to show you how to predict the rate law and figure out the value of the rate constant given an equation and a data set for that equation with 3 different experiments. So commonly figuring out the rate and the rate constant is usually what they'll have you do. It's usually on every test. So that being said, you're given an equation. Sorry, there's a 2 here. And they ask you to just figure out the rate law, and the rate constant, right? Usually the problem with this is that people are a little overwhelmed when they're given an equation. They ask 2 things of you, so kind of you have to do step by step. What they mean with the rate law is they need you to figure out the rate, the orders of reaction for both of the variables involved. And the general formula for the rate law is rate equals K, your rate constant, times the concentration of both of your variables. So in this one, this is the general one. I'll just do A and B. And we usually do M and N for the exponent, so I'll keep that the same. Right? So in this case, I'll just do F2 as my first one, and ClO2 is my first one. These are the reactants. They go right into the rate law here. Right? So now we also have 3 different experiments that we're using. And we have different concentrations for ClO2 as well as the initial rate of reaction. Right? So in this case we have 0.1, 0.2 here, and then we start off with 0.01, 0.04, 0.01 again. And we have 1.8 times 10 to the negative third, 7.2 times 10 to the negative third, and 3.6 times 10 to the negative third. Now, to figure out the order of reaction, basically what the order of the reaction is, it's an exponent on the rate law, and it directly affects the concentrations and how they affect the rate of the reaction. If it's 0, it has no effect on the rate of the reaction. We can quadruple, we can do anything we want to the concentration of one of these, and if it's 0 order, it's not going to affect my rate. Now, if it's first order, it's a 1-to-1 ratio. If I double this, the rate is doubled. If it's second order, it's shown more as an exponent. So remember, if I double it, and the exponent is a 2, well, now instead of doubling my rate, it's actually going to quadruple it, right? So you can see that if the exponent's bigger, the variable in question is going to have a bigger effect on the rate of more magnitude, of course, because the bigger the number of the exponent, the bigger the number of the exponent, the bigger the difference it's going to make when we alter the concentrations of our reactants here. Now, I'm going to start trying to figure out the orders of the reaction. First, we're going to start with fluoride. And a good rule of thumb is that you're going to look to isolate the variable and do one at a time, right? We're not going to try to figure out both orders at the same time, because then we don't know which one affected the rate more or in what portion, or if either of them did, right? So if we look at 1 and 2, for example, fluoride is kept the same, 0.1 and 0.1, whereas ClO2 is quadrupled. It goes from 0.01 to 0.04, right? So like I said, similarly here, this is a very simplified method of looking at how the concentration affects the rate. So if we go from 0.04, or from 0.01 to 0.04, right, we're going to do the second one over the first. And once again, this is for ClO2. And how it affected the rate, which is going to be 7.2 times 10 to the negative third for the second instance, and 1.8 times 10 to the negative third for the second, or for the first, sorry. And once again, you're going to see it like this. So to figure this out, we're looking for the variable that's here. In this case, we'll call that n. And as you can see, this is going to simplify to 4n. And if you do this in your calculator, this will actually go down to 4. Now, the only thing we have to do is solve for n. And in this case, 4 to the what power equals 4? Well, then that means n is 1, right? Now, if we do the same thing for F2, once again, we're looking to isolate F2. And we're looking for it changing, whereas its counterpart isn't. So if you look at experiments 1 and 3, F2 is doubled, whereas ClO2 is actually kept the same. So if I do the same thing, 0.2 over 0.1, right? Second over the first. And then we're going to do the same thing for my rates of the reaction. So it'd be 3.6 times 10 to the negative third over 1.8 times 10 to the negative third. Right? Once again, my variable's here. This one's going to be m. So it's 2 to the m power equals 3.6 times 10 to the negative third divided by this. So this actually simplifies down to 2. And once again, my order of the reaction over here is going to be 1. Right? So both of my exponents are 1s. So we have the first part finished, right? These are both 1s. So if I was to write the rate of this, I would write rate equals k, and then instead of writing m and n, I could either write the 1s or leave them blank, right? So now we just have to figure out our k. Now to figure out k, it's actually quite simple if you have a data set. Since you have instances or experiments where you have a concentration and a rate law and initial rate. So what you do is you would just plug it in to see what the rate constant is, because since the rate is constant, even if you only have an initial rate, that's sufficient enough to figure out k. So I would plug it in. For example, if I use the first one, it would be 1.8 times 10 to the negative third, and you would just put in the concentrations for A and B, F2 and ClO2. So it'd be 0.1 and 0.01. And once again, the exponents play a bigger role when they're not 1. In this case, I'll write them in just for the sake of correlating it to the general rate law. But if they're 1s, I usually don't even write the 1s. Now you just solve for k. And in this case, k is going to equal 1.8. And the units on that would be molar and s. And they're both going to have negative exponents because of the way that the units sorted out when you divided them. Right? Because the rates, the initial rate units is molar per second, and these are usually in molar. So when you solve for k, those are the units that you need for it to cancel out effectively. And that's my presentation on how to figure out the rate law and the value of the rate constant. Thanks for watching.